Two arrays, same values, same shape, same code. One is fast, the other is mysteriously slow. No algorithm changed, no math changed, and nothing obvious changed, and yet performance collapses. If you've ever had NumPy code that suddenly got slower after a reshape or a slice or transpose, this is the reason. The explanation has nothing to do with NumPy tricks and everything to do with how memory is laid out. In this video, we are not talking about the syntax. We are opening the array and looking at what actually exists in memory. Once you see that, NumPy's behavior stops being confusing and starts being predictable. At first glance, a Python list and NumPy array look like the same thing. You print them, you index them, you loop over them, and so on and so forth. If you didn't know better, you would assume there are just two ways of storing a bunch of numbers. You want to believe NumPy is just the faster list. Same idea, better performance. Something like Python list but optimized. That belief seems reasonable, but unfortunately it's wrong, because the moment you look at how these two are laid out in memory, that idea completely falls apart. Let's start with a familiar one, a Python list. When you write this, it feels like you created 4 numbers in a row, but physically that's not what exists in memory. A Python list does not store numbers, it stores references. What you actually have is one array of pointers, and each pointer refers to a separate Python integer object somewhere else in memory. Each of those integer objects has its own metadata and its own identity. The list itself doesn't own the data, it only knows where the data lives. This design gives Python flexibility. You can mix types, you can resize the list, you can replace elements freely, as you see in Python. But that flexibility, of course, comes at a cost. You lose control over the memory layout. Now let's look at the NumPy array. This looks similar when you print it, but physically it's the opposite of the Python list. A NumPy array allocates a single contiguous block of memory. Inside that block are 4 64-bit integers, stored back to back with no gaps and no per element objects. This is not an optimization detail. This is the foundation. Because NumPy owns the memory, it can make strong promises about the layout, and those promises are what enable speed. Now here's the conflict. If a NumPy array is just one block of memory, how can it support slicing and reshaping and multiple dimensions without copying data every time? The answer is that the NumPy array is not just data. It's a description of how to interpret data. Every NumPy array is defined by 3 things: a pointer to a memory, a shape, and a stride. The pointer tells NumPy where memory starts. The shape tells NumPy how many elements exist in each dimension. The stride tells NumPy how many bytes to jump to reach the next element along each dimension. A stride is the key idea that makes everything else make sense. Let's look at the slicing. In a Python list, slicing creates a new list and copies elements. In NumPy, however, slicing usually creates a view. No data moves. NumPy simply shifts the pointer and updates the shape. Both arrays now refer to the same bytes. That is why this behaves the way it does. This surprises people because it feels unsafe, but it's not really unsafe, it's kind of honest. Both arrays describe the same memory. This leads to a common myth. A stride becomes even more important when dimensions enter the picture. This looks like a 2-dimension grid, but physically it's still one linear block of memory. NumPy uses shape and stride to reinterpret that blocks as rows and columns. Now watch what happens when you take a column. That column is not contiguous in memory. NumPy doesn't move data. It creates a view with a larger stride. To move from one element to the next, NumPy jumps across the memory. The values didn't change. The shape didn't change. Only the stride changed. And that difference alone can make code dramatically slower. Two arrays can look identical when printed, but they can behave differently at the hardware level. This same mechanism explains reshaping. As long as the existing memory layout supports the new interpretation, reshaping is essentially free. NumPy just recalculates shape and stride. Python lists cannot do this. Lists do not own a predictable block of memory. Once you store references, layout is no longer under your control. Here is the change in perspective that matters. A NumPy array is not a container. It is a contract about memory. Shape and stride describe how to walk through that memory. Operations are defined by traversal, not by structure. Once you see arrays this way, NumPy's behavior stops being confusing. Shared memory stops feeling dangerous. Reshaping stops feeling magical. Performance differences stop feeling random. This leads us to the result. NumPy is powerful powerful because it exposes memory instead of hiding it. That exposure enables zero copying slicing, cheap reshaping, and predictable access pattern. It also requires you to understand what you are working with. And with that, good morning, good afternoon, and good evening. Bye.